Hi everyone. Today I'm going to be talking about generic external memory architecture for programmable switch data planes. So today's data centers widely deploy merchant silicon switches because they are cheap and widely produced. However, they have very limited amount of SRAM space, which is typically tens of megabytes. Now I explain how such limitation can be bottleneck for memory-intensive network applications using an example called bare metal hosting service in clouds. In this service, customers can install their bare metal servers in the public clouds, and the cloud providers such as Azure needs to provide a virtual switching between bare metal servers to their customer VMs. You know that network virtualization have been relying on software switch running on hypervisor, and such hypervisor switches have used enormous amount of DRAM on the servers. However, in bare metal service, you cannot trust bare metal server, so you cannot install any virtual switches on the servers. So the only available solution is to move virtual switch functionality to top-of-rack switch. Unfortunately, top-of-rack switch does not have enough memory to store virtual switching table, so the Tor switch cannot perform as a virtual switch. So how do you solve this problem? So this example illustrates limited switch memory space can be problematic for memory-intensive in-network applications. In fact, there are many use cases that can benefit if the switch has larger memory. We observed this emerging pattern where both research community and industry have proposed to move rich functionality to switches. One example is moving stateful load balancer for hundreds of millions of flows connections, which is typically backed by large DRAM, to switches. And network monitoring is another example. So flow level monitoring like NetFlow is an important application, but cannot be implemented on switch because of limited memory space. Also, given the flexibility of data plane programmability, people are thinking of offloading part of computing to switches. Examples are key value stores and consensus and coordination protocols. With more memory, key value cache hit rate will increase and coordination service can serve more nodes. Obviously, with more memory on switching chip, you can make your network a lot powerful and you can even run a lot cool applications. Why is adding DRAM for switches particularly important and useful right now? This is because now in the networking world, we have a new technology called programmable data plane, and we have this new switch architecture called PISA, which offers flexible programmability, but which has only limited SRAM cache. Imagine that you have x86 CPU only with a cache without any DRAM. What kind of application you can run there? How limited is your choice? In the programmable networking world, we are exactly in that position. We only have limited on-chip SRAM cache, but we don't have any DRAM so far. So if we have DRAM for programmable switching chip, we can easily expect that it'll improve many existing in-network applications and also realize many innovative applications in the future. So by now, I probably convinced you that adding more memory is important for programmable data plane technologies. If you look at the spectrum of switching chip, it's not that we don't have any chip that can use external DRAM. In fact, some expensive fixed function switching chip are built and designed to be able to take advantage of external DRAM. Such chip access external DRAM located on the same switching board through numerous DRAM modules and controller installed within the chip. However, this approach is very limited, so it's not that useful in practice. The memory can be used only for the fixed function, which is chosen at the chip design time. And also, the total amount of DRAM you can put is fixed, again, at the chip design time. Also, it's expensive because the chip gets larger and complex due to additional wires and additional modules. So our question here is it possible to have general purpose DRAM for programmable switching ASICs without chip modification? To answer this question, we are proposing GEM, General External Memory Architecture for Programmable Switching Data Plane. In GEM, instead of attaching a separate DRAM to switching board, we actually decided to reuse server's memory in data center. We realized that servers that are directly connected to Tor switch have huge amount of DRAM, and servers really do not use all these DRAM all at the same time. Key advantage of this approach is that it's very cheap, flexible, and readily available. So it just reuses existing commodity hardware in data center without adding additional infrastructure cost. Also in GEM, you can adjust the amount of bandwidth to access remote memory at runtime. For example, you can choose 1 gigabit per second or multiple hundred gigabit per second depending on your memory demand. Essentially, GEM introduced the notion of memory hierarchy for switch data plane. So you can use on-chip SRAM as a cache and remote memory as a main memory, just like in memory hierarchy in CPU architecture. So how can you realize this vision? Specifically, we need to solve 3 problems. Suppose that the switching chip now can access remote memory through our GEM architecture. When the lookup miss happens, the switch will try to look up the remote table. For this, we need an access channel that allows the data plane to access remote memory with low latency. Also, if the data plane wants to modify packet based on the remote contents, the data plane may need to keep the packet during the remote memory access. Lastly, we need a remote data structure at corresponding API so that the data plane use the remote memory data structure just like as a local memory data structure. So how to enable the switch data plane to directly access remote memory? Especially, it has to access purely DRAM, making no impact to servers' existing compute or networking workloads. Also, it needs to achieve minimal latency between the chip and the memory. But there's no obvious way to connect the chip and memory. The chip only has an Ethernet as an external interface, and the memory has a DDR as its external interface. So to enable the direct DRAM access from the chip, we need somehow to translate Ethernet directly into DDR. And guess what? We already have such technology. It's called RDMA, or Remote Direct Memory Access. An RDMA NIC on a server can receive and process RDMA request from the switch and send the response back to the switching chip without involving any server CPU. And a good thing is many data centers have already deployed this RDMA NIC on their server, so we can just reuse the existing infrastructure. A key challenge here is that generating RDMA requests from the data plane, because programmable switching chip cannot generate arbitrarily new packets. So how can you solve this? Since the data plane cannot generate arbitrarily new packets, we decided to reuse incoming packets that triggered remote memory access. To generate RDMA request, we clone and truncate the incoming packet and add RDMA header on top of it. Also, to manage a reliable RDMA connection with remote servers, we let the data plane to maintain a minimal set of RDMA connection state, including QP number and the packet sequence number. The good thing is all these features can be implemented in P4. Now, the switch can access remote memory via RDMA. Then how can you manage the packet during the memory access? Now, while the switching chip can issue RDMA request, here's a potential problem. What if the data plane needs to modify the packet based on contents fetched from the remote memory? A strawman solution would be buffering a packet during a remote memory access and wait until it receives the response from the remote memory. However, buffering a packet can consume large SRAM space and also cause other issues such as packet drops. To solve this problem, we propose simple but effective solution. Before sending an RDMA read request, we first store the incoming packet to the remote memory, and then read both the table entry and the packet back together. This way, the data plane can modify the packet with the remote table entry without using additional SRAM space. The last component is remote data structure in remote memory and APIs to access it. In this example, to look up an entry from the remote lookup table, the data plane needs to know the remote memory address corresponding to the entry key. One straightforward solution would be to store a mapping between all possible keys and remote memory addresses on chip SRAM. However, it would consume a huge amount of SRAM space, which is undesirable. So, how to efficiently extend data structures such as lookup table to remote memory and support operations such as lookup and update without consuming many SRAM space? This is one of our open questions, and we are currently exploring a design space to find a general data structure and abstractions for remote memory. As a preliminary design, we extend three data structures called lookup table, packet buffer, and state store for three specific applications. Let me bring back the bare metal service example. Using our lookup table extension, we can realize the service using the top of rack switch. We can store an entire table on remote memory as a remote lookup table, and the switch can access to fetch the entry when the entry does not exist in its local table. In this way, we can effectively move the virtual switch functionality to the top of rack switch. As other use cases, we can use packet buffer extension to mitigate packet drops when incast happens by buffering and loading packets from remote packet buffer. Also, with state store extension, we can store flow state information such as TCP statistics, per flow TCP statistics to remote state stores when it needs to maintain huge amount of information. To verify the feasibility of our approach, we used a testbed consisting of 3 servers connected to a programmable switch. We implemented remote memory extension and corresponding primitives as P4 actions. And in this specific experiment, we measured the additional latency caused by accessing remote memory. The P4 program we wrote fetches an entry from the remote lookup table for all incoming packets and applies the action to each packet and forward it to the destination. We ran a simple L2 switch implementation as a baseline. This figure compares the median end-to-end per packet latency when packets traverse the baseline and the prototype data plane. Here, the x-axis is the packet size, and y-axis is the latency. We can see that accessing remote memory as less than 2 microseconds on average, which is mainly caused by RDMA latency and data plane logic. Also, in another experiment, we confirmed that the data plane can store and load MTU-sized packet at near line rate. So overall, limited memory space on switch is problematic for in-network computing. To solve this problem, we propose a new generic external memory for programmable switch data planes, which is cost-efficient, flexible, and readily available. I conclude this talk with a number of open questions regarding our approach. First, designing an efficient caching mechanism is important. To minimize the access latency, we should efficiently cache a part of remote data structure on on-chip SRAM. Also, to serve dynamically changing workload, managing and scaling remote memory pool in real time is another important issue. Lastly, handling switch or server failure efficiently is another open challenge. By answering these questions, we hope GEM architecture will be a key enabler for future in-network computation and in-network applications which require larger memory. With that, I'm happy to discuss any of these open challenges and take any questions. Thank you.
Brad Park, UCL. I really enjoyed your talk. I wanted to ask you about Q1, but not about the way you phrased the question. What you said is that the development of a caching mechanism for SRAM. The first thing I thought early in your talk when you showed us all those paper titles of systems that want more memory on switches was, what's the working set size for those applications? Because it seems like we don't even need to know what the design of the underlying remote memory access protocol is. The first question I would want answered is the SRAM big enough for the working set size for the kind of applications that you're thinking about? So I just wondered, like, for the range of applications that you mentioned as the motivation, do you have a sense of what the working set size is?
Yeah, so for instance, I think that's a good question. So for instance, the varimeter service case, the entire virtual switch table size is like, it needs to maintain like around 10 billion the table entry, which is around like more than 30 megabytes, for instance. But the SRAM size is less than that, right? But the thing is, the hot entry size is like less than the actual SRAM space. So if we can maintain the hot entry means like flow, I mean the frequent flow. The number of frequent flow entry is less than, the size of that entry is less than the size of SRAM, that we can fit that portion on the SRAM.
Great, yeah. No, so I think that's great. So it sounds like there are examples where the working set fits. I guess the question is, for the full range of applications you used as motivation, do you think the working set fits for all of those? Or which ones do you think are the ones where it might not fit?
So for instance, like a network monitoring case.
Yeah.
That case, I think in that case, we need to update all the flow information to remote memory, not on the SRAM space.
Right.
Because there is no like a hot entry, concept of hot entry in that case. So I think in that case, for every packet or every flow, we need to update the remote memory instead of using caching mechanism.
Okay.
But for lookup table example, we can at least cache the part of entire table.
The hot part, yeah. Thank you.
Okay. So Craig Partridge, Colorado State University. So first a quick comment and then a question, which actually follows up on your observation about the data. But before that, when you talked about imagine using an x86, early internet devices, many of us programmed were x86s with 500 kilobytes of memory. You can do a whole lot with those. Just, you have to be smarter, but it's not a good example of what you can't do, since it's how we built the internet. But at any rate, moving forward on this, you talked about all the data that you actually are collecting as measurement data. And that raised the question, two questions. One is, that suggests you want to have a NUMA architecture, and I don't remember whether RDMA actually supports non-uniform memory access, times, because for pushing data, you don't really care a whole lot about the latency of the write. But it does, so the question is, can you do that? And the other one is, it begs the question of having a shared memory, because you can then have somebody else maintaining your tables or collecting your measurement data from your DRAM pool, so it doesn't have to be managed by the switch. The switch just pushes the data there or retrieves information from the table, and some third-party device is actually the thing that's maintaining the memory and maintaining the tables for it. Have you thought at all about the challenges that you get if you start to have those kinds of lockout rules and other sorts of things in your memory system?
Yeah, so the basic model here is, so the network operator, which wants to use this architecture, install some RDMA agent on the server side.
Okay.
Then that agent program, daemon, register some portion of memory pool. I mean, the DRAM pool.
And I'm not familiar. Does RDMA allow that to be shared so you can just allocate it and have multiple writers at the same time?
Multiple writers at the same time.
Multiple writers or one writer, multiple reader architectures? Because that's for doing it in that memory.
Multiple writers.
So RDMA has RDMA CAS.
Okay.
So there is this notion that it could be shared, but there's atomic operations that are more expensive that you have to use.
Okay. So the answer is you could do it.
I think so.
Okay. Because that would be an interesting thing to be able to do.
Thanks.
Hello. Yeah. Good morning. Kenji from China Mobile Research. I don't know. Your paper is promoting like a programmability through P4, or you are looking at dynamic resource pooling. The thing is, if you look at the Intel rack scale design, that solution is already providing whatever you have provided in your paper, except the programmability itself. That is P4. So what is the main purpose of your paper? Programmability or dynamic resource pooling? Thank you.
So I think the main goal of this work is provide a flexible DRAM pool to switch data plane.
If you look at Intel RSD, probably is providing the similar functionality as whatever you are providing.
Okay, I see.
Enjoyed your talk. A couple of sort of generic questions. One is, I was wondering, are there any lessons for just the RMT architecture, or what little additional functionality you could add to make some of your life easy with respect to supporting this particular model of using having generic external memory? Do you have any ideas on how you would change
existing our RMT architecture
Yes.
to support this architecture
Minimal
more
changes.
naturally? So I think so. One thing we did was so one of the idea we presented was to reroute the original packet to the remote memory to avoid the packet buffer during the remote memory access. So if the RMT architecture supports some like temporary packet buffering or some packet buffering during the remote memory access, then it would be better. It would be more like natural solution to during the remote memory access. Yeah.
Okay. So my second question, we can follow up. I have some thoughts on how, on the first part. The second question I had is, the focus seems to be on sort of intra data center applications. Have you thought about the WAN at all? Like, does it make sense to think about doing RDMA-like stuff between WAN routers and some collection of hosts that may be co-located, or clusters of computation that may be co-located with routers, or something else? Is there any application?
So I think the key problem in using RDMA in WAN environment is like latency.
Right.
So
but you could imagine using it in sort of a hop-by-hop fashion. You don't have to do it purely.
You mean inside the data center? For
some sort of a cluster co-located with some subset of your routers, like a compute cluster.
We can also use the same, similar architecture for that case. But if the number of hops between the switch core router, for instance, and the DRAM server is large, then the RDMA latency will be increased.
I understand. Okay, thanks.
Yeah, thank you.
Why don't we give the speaker another hand?